separately excited DC generator. In the given figure, Vt is the terminal voltage across the load measured in volts. Eg is the generated voltage at the armature terminals measured in volts. Ia is the armature current measured in amperes. IL is the load current measured in amperes. If is the field current measured in amperes. Ra is the armature resistance measured in ohms. Rf is the shunt resistance measured in ohms. Now, armature current Ia is equal to IL. Terminal voltage Vt is equal to Eg minus Ia Ra. Electric power developed is equal to Eg Ia. Power delivered to load Via is equal to Eg minus Ia Ra multiplied by Ia, which is equal to Eg Ia minus Ia square Ra. Separately excited DC generator. This DC generator has a field magnet winding which is excited using a separate voltage source like battery. The output voltage depends on the speed of the rotation of the armature and field current. The higher the speed of rotation and current, the higher the output of the EMF. Self-excited DC generator. The self-excited DC generators are classified as follows. Click the tabs to know more. DC series generator. In a series DC generator, the armature winding is connected in series with the field winding so that the field current flows through the load as well as the field winding. Field winding is of low resistance and a thick wire of few turns. Series generators are also rarely used. In the given figure, armature current Ia is equal to Ise is equal to IL is equal to I. The terminal voltage Vt is equal to Eg minus I multiplied by Ra plus Rse. Power developed in the armature is equal to Egia. Power delivered to load is given as Egia minus Ia square multiplied by Ra plus Rse, which is equal to Ia multiplied by Eg minus Ia of Ra minus Rse, which is equal to Vtia or Vtil. DC shunt generator. In a shunt DC generator, the field winding is wired parallel to the armature winding so that the voltage across both of them is the same. The field winding has high resistance and more number of turns so that only a part of the armature current passes through the field winding and the rest passes through the load. Shunt field current IF is equal to Vt divided by Rf. Armature current Ia is equal to IL plus If. Terminal voltage Vt is equal to Eg minus IaRa. Power delivered in the armature is equal to Egia. Power delivered to the load is equal to Vtil. DC compound generator. In a compound DC generator, two types of field windings exist, namely Rf and Rse. They are basically shunt winding and series winding. Short shunt. The shunt field winding is wired parallel to the armature and the series field winding is connected in series to the load. Short shunt series field current ISE is equal to IL. Shunt field current IF is equal to VT plus IS ERSE divided by RF. Terminal voltage VT is equal to EG minus IARA minus ISERSE. Power developed in armature is equal to EGIA. Power delivered to the load is equal to VTIL. Long shunt. Here the shunt field winding is parallel to both armature and series field winding. Long shunt series field current ISE is equal to IA, which is equal to IL plus IF. Shunt field current IF is equal to VT divided by RF. Terminal voltage VT is equal to EG minus IA multiplied by RA minus RSE. Power developed in the armature is equal to EGIA. Power delivered to the load is equal to VTIL. Magnetization and load characteristics of DC generators. The most important characteristics of DC generators are open circuit characteristics and load characteristics. Click on each tab to know more. Open circuit characteristic can also be called as no load magnetization characteristics or no load saturation curve. This curve shows a relation between the generated EMF at no load and the field current at constant speed. The data for open circuit characteristic curve is obtained experimentally by operating the generator at no load and constant speed and recording the change in terminal voltage as the field current is varied. Load characteristic or load magnetization curve. This curve shows the relation between the terminal voltage and field current by keeping the armature current and speed constant. Magnetization and load characteristics for different types of generators. The different types of DC generators are shown below, and their operating characteristics are discussed in further slides. Separately excited generators. The operating characteristics of DC separately excited DC generators are no load characteristics or open circuit characteristics and load characteristics. Click on each tab to know more. No load saturation curve, EG versus IF. It is a plot of EG with respect to IF at armature current IA equal to 0 and speed N is constant, and its graph is shown below. Conditions. There should not be any load, that is IA is equal to IL, which is equal to 0. The armature is driven at rated speed by the prime mover. The field winding is energized, that is, apply DC source to the field winding, then field current IF is increased in steps. At each step, EG and IF are recorded by using the voltmeter and ammeter respectively. Field current IF is increased till EA is about 1.1 to 1.25 times the rated voltage VT. Even though if we don't apply any energy to the field, the voltmeter indicates a small voltage, that is 2 to 6 volts. This is because of the residual flux in the main poles. In the graph, it is shown as OA. Observations. Till AD, the curve is a straight line because the entire field MMF is almost spent in forcing the flux through the air gap, and the MMF required by the ion is almost negligible. From D point to C, there is a decrease in generated voltage rather than an increase. It is because at certain value of IF, that is field flux, saturation sets in and MMF required by the ion increases more rapidly than the flux. Hence, D point is called knee point of no-load characteristics. Load characteristics. Load characteristic is a plot of Vt on y-axis and If on x-axis with constant Ia and speed. Procedure. To plot the graph, run the armature at a constant rated speed and close the switch S. Adjust the field current till Ia is equal to the rated armature current. Since we are applying load, it is called load characteristics. Take the readings of a voltmeter V and ammeter A1 and A2. Vary the load and field currents in such a manner that Ia remains constant but terminal voltage Vt changes. Repeat the process till sufficient readings are taken. Make load resistance to 0, that is dead short circuit, therefore Vt is equal to 0. So point A on the load characteristics is obtained. Note: both no-load and load characteristics follow the same shape, but load characteristics are a bit less in value due to armature reaction effect. DC shunt generators. The important characteristics of DC shunt generators are no-load characteristics or open circuit characteristics or load characteristics. Click on each tab to know more. No-load saturation curve Eg versus If. This characteristic for the self-excited shunt generator can be plotted with the help of a connection diagram as shown on the screen by keeping the switch S open. If the field winding circuit of the shunt generator is disconnected from the armature circuit and separately excited, then the no-load characteristic with separation excitation will not differ from that obtained with shunt excitation. This is due to the fact that a small amount of current flowing in the armature of the shunt generator has negligible effect on the main flux. It will rather be more convenient to run the shunt generator as a separately excited generator for obtaining its saturation curve. The saturation or magnetization curve so obtained can be used for shunt generator analysis without any appreciable error. Load characteristics. The load characteristic is obtained in the same manner as for the separately excited generator. Actually, the load characteristics obtained for both separate and shunt excitation are the same, and it is shown on the screen. The slight difference is due to the different armature currents. Ia is equal to the sum of IL and IF for shunt generator, and Ia is equal to IL for separately excited generator. Different armature currents result in different armature reaction, giving slightly different voltage drops in the two cases. This is defined as a relationship between the terminal voltage and the load current. This graph is the same as that of the load characteristic curve obtained in the case of a DC shunt generator. series generators. The important characteristics of series generators are given below. Click on each tab to know more. No-load characteristics or open circuit characteristics. We know in series generators, field winding, armature winding and load resistance are connected in series. Here, IL is equal to IF, which is equal to IA. As all the windings are connected in series, the no-load magnetization curve can only be obtained by separately exciting its field winding from a low-voltage source as shown in the figure, and IA is equal to 0. Load characteristics. To get these characteristics also, the series field winding should be separately excited. The shape of the characteristics is same as that of a separately excited generator as shown in the figure. The important characteristics of compound generators are given below. Click on each tab to know more. No-load characteristics or open circuit characteristics. For a long shunt compound generator, same current flows through the series and shunt field turns. The number of series field turns is far less than that of the shunt field turns. So the effect of series field MMF may be neglected in comparison with the shunt field MMF at no load. For a short shunt compound generator, series field carries no current when obtaining its no-load characterization. Thus, the no-load characterization of long shunt or short shunt compound generator is same as if it were a shunt generator. To get these characteristics, the series field winding should be separately excited. The shape of the characteristics is same as that of a separately excited generator.